Hello, welcome back to physics. Here we're going to start the first part of a set of lessons on freefall motion problems. So you should have an idea about what gravitational acceleration is. We call it g. It's 9.8 meters per second squared acting down. We talked about that a lot. And now we're going to be solving problems that deal with objects that fall. And basically what we're going to do is use the exact same equations that we've used before for constant acceleration. Because, you know, when we have v naught t plus 1/2 at squared, for instance, in one of our equations of motion, a in this case now is just the acceleration due to gravity. So you're really going to use the exact same equations that we've used before, but applied to falling objects. So we'll have some things to talk about along the way, but that's essentially the big picture. So to write that down and make sure you're 100% clear, we're going to use the exact same equations of motion as we did before. We're going to make a couple of changes. We're going to replace the acceleration a with negative g, where negative g is negative 9.8 meters per second squared. The reason it's negative is because we're going to take falling downward to be the negative direction, and we're going to be taking upward to be the positive direction. So if you ever get negative velocities, it'll be going down, and positive velocities, for instance, will be going up. And that's just a convention. That's how we're going to do it, and that's why we have a negative in front of the 9.8 meters per second. The other thing we're going to be doing in order to change our regular equations of motion into free fall equations is we're going to label position. We're going to use the variable y instead of, this means instead of x. And that's just a convention, because typically before, when we're talking about cars going or something like that, it's horizontal motion. Horizontal motion usually is, we call it x, because you can think of an xy plane. X goes this way. But when we have objects going straight up and down, which is what we're doing in free fall motion, that's typically what we call the y direction. So just like an xy plane, positive y is up, negative y is down, and so on. So we're going to be using the variable y instead of x just because free fall motion has motion that goes up and down. And the third thing we're going to have that's going to change things a little bit is motion starts at y equals 0. In other words, typically whenever you're dropping something, you let go from a position, and we're going to call that position 0. Just like in all of our other problems, we had some time where things started. We called that x is equal to 0, and then we're going to have y is equal to 0. And then, of course, I already told you going down is going to be negative y, going up is going to be positive y. So if we really wanted to drill this in, and we do want to drill it in, make sure you understand, we're going to draw a little picture. It's going to be a very simple picture. Let's say there was a ledge or something, like a building or something, and it has a ledge out here. You're standing up on the edge of the ledge, right? And you drop a rock, like let's say from this position here. Here's a rock. You drop it, it's going to go down. All right. What we're saying by all this stuff is that this is the up and down direction. So when we drop the ball, it's going to be going in the y direction, being y, positive y being up and negative y being down. But the exact location that the motion starts, we call it y is equal to 0. Or you can say y naught is equal to 0. That's the initial position of the rock, is the 0 point. You have to have some point being 0. And then what we're going to say is that this direction going down, we call it negative y direction. So all of our positions are going to actually be negative. But when you get a negative 5 meter position, it's not a crazy answer like another dimension or something. Negative y just means that it's below your starting point because gravity pulls things down. And I don't have much room up here, but there's an up direction here that we call, of course, positive y. So that would be a case, for instance, if I'm standing on the ledge of a building and I throw something straight up, then initially the position of the ball will go in the positive y direction. Eventually it'll slow down, turn around, and start going in the negative y direction once it gets down close to the ground. So that's kind of our convention that we're going to be using. And it's incredibly important for you to understand that. Now the next thing we're going to do is we're going to talk briefly about the equations of motion, and then we're going to solve a quick problem, just to kind of get your feet wet with how do we use these things. Now, if you remember, the main equation of motion for position is x is equal to x naught plus v naught t plus 1/2 at squared. We've used it a million times. But because we're doing free fall motion only in this direction, it's actually going to look like this. Y is equal to y naught plus v naught t plus 1/2. And it's going to be acceleration times time squared again. So the way I want you to think about this is at squared. Now, we are talking about gravity, so we are going to put the gravitational acceleration in here. But for now, just think about the fact that you have motion in the y direction, some initial position, usually 0 where you drop the thing from, initial velocity, 1/2 at squared. This equation of motion for position is the exact same equation of motion that we used for constant acceleration before. So in physics, I guess what I'm trying to say is there's oftentimes students will see all the equations and start getting really worried that there's so many of them, and they're all different. So you see constant acceleration with x's, and then you see free fall motion with y's, and you start getting confused, like, why do we have extra equations? Well, they're not different. They're the exact same equation, right? It's just that in this case, when we drop an object, we use the positions, we call it y because it's going up and down, and we're actually going to take care of this now. We're going to talk about this. We're going to put the gravitational acceleration in here. So what I like to do is just write this equation down, and then whenever I go to the next step, what I end up doing is the following. I'll say y is equal to y naught plus v naught t plus 1/2. Now, for these free fall problems, the acceleration is always negative 9.8 meters per second squared, t squared. You have to put a negative in here, because if you don't put a negative, it means the acceleration is going up. And you know when you drop objects, nothing accelerates up, it always goes down. So you have to have the proper sign, because the down direction is the negative y direction. So the acceleration must be acting in the down direction. So when I solve a problem, I will write this equation down, and then in the next step, I'll put in everything I know, and just like any problem, I'll stick the gravitational acceleration in there. But for some reason, some physics books like to show you something like this. They'll give you the equations of motion for free fall, and it'll look like this. V naught t, and what you'll get here is, since they know that the acceleration of gravity is negative 9.8, you'll write it like this, negative 1/2 g times t squared. And this is where students, I think, start to get confused, because they see this equation, and it looks kind of like a constant acceleration equation, but it's different because it has a g in here and there's a negative sign here. So you look at it and you're like, well, this is different than the other case. Well, it's not different. I am not really going to use this form of the equation because I think it's misleading. What I would rather say is that we're using the exact same equation as before. Nothing has changed. We're just relabeling the position variable, and we're going to stick the proper acceleration in here, which just so happens to be negative 9.8. So I don't have to memorize a new equation. That would be silly, because it's the same equation. So if your book has something like this, you can use it. It's fine. Just stick 9.8 in here. But just know that it's exactly the same equation that you've been using all along, with a negative 9.8 thrown in there. Okay? So what I'm going to end up using is this equation right up here at the top. I'll stick a negative 9.8 in there. All right, so this is the position equation of motion that we're going to be using all the time. Now, what's the other equation of motion that we typically use for velocity? It's v is equal to v naught plus a times t. This is the equation of motion we've used for every constant acceleration problem. But because we know that when we drop an object, this acceleration is really negative 9.8, what I will do is I will write this equation down, and then the next step I'll say v naught plus negative 9.8 times time. Just like any other problem, you stick the acceleration that you know in there, which is negative 9.8. But again, some books like to write this as the following. V is equal to v naught. Since it's negative, they'll put a negative g times t. So you might see this equation in your book. If you see it, it looks to be different than the other equations of motion we've been using for the same reasons. It's got a g and it's got a negative sign. But don't memorize a new equation. You use the exact same equation that we've been doing. You just stick the proper acceleration in, which is negative 9.8 for gravitational freefall. And then finally, it's the exact same deal you can guess for the third equation of motion. V squared is equal to v naught squared plus 2a. Now, usually it's x minus x naught, but since we're dropping things, it's going to be y minus y naught. So we're just relabeling x to y. All right, so this is what I will do for my problems. I will just write this down, and then in the next step, I will stick the proper acceleration in there. So I'll write down v squared, v naught squared, plus 2 times a, which is negative 9.8, times y minus y naught. But again, lots of books like to take something like this and pretend that there's a new equation of motion, which is, in my opinion, confusing for students, and they'll do something like this, minus 2 times g times y minus y naught. So again, you have an equation with a negative sign and you have a g. So I guess what I'm trying to say is your book might have this equation in it, right? It might have this blue equation in it for free fall. It might have this blue equation in it for free fall. If you want to use these equations, fine. Minus 2g y minus y naught, no problem. Just stick a 9.8 in there and you get exactly the same thing. But instead of telling students that there's an additional set of equations to memorize, I prefer to tell them, no, it's exactly the same equations we've always been using. We just stick the proper acceleration in for A. All right? So now I think we are ready to solve our first very simple problem. This will be pretty easy. We're going to ramp up the complexity as we go, as we always have. But all of these problems will be dropping things from a certain height. So you want to typically calculate how far it goes, how fast it's going, how long it takes. So we've done problems with acceleration in the horizontal direction before with constant acceleration. And now we're doing problems that go up and down. And then the roadmap is, after we master this, we will tackle things that go in a curved path, like throwing a baseball. Because anytime you throw a baseball, or a football, or a basketball, this curved motion can be broken up into a horizontal component of the motion and also a vertical component of the motion. So now we're learning how to tackle vertical motion. We already know how to tackle horizontal motion, so once we master this together, we'll put them together and we'll make curved path motion. That's how we get to what we call projectile motion down the road. So let's go ahead and do this now. The first problem, if I can get to the problem, is very simple. It says a ball is dropped from a very tall tree. What position and velocity of the ball, what is the position and velocity of the ball after 1 second, 2 seconds, and 3 seconds after the drop, and neglect air resistance? So that's something I need to tell you now anyway in general, is you're always going to neglect air resistance, okay? You pretend there's no air. Later on, we're actually going to talk a little bit about air resistance, but for now, we just always pretend there's no air there at all so we can calculate things perfectly. So we drop a ball. Where is the position and the velocity? What is the position and velocity after 1 second, 2 seconds, and 3 seconds? So as always, we are going to draw a picture. So it's a very tall tree. You know I can't draw anything. So here's a tall tree. That's a pretty good tree, I think. But this tree is a weird tree. It's got a branch that goes out here. Why do you think it has a branch out there? It's because there's a person standing on it. Of course, he's going to drop something, right? And he's going to drop something straight down. So he reaches out, he or she reaches out, and there is going to be a ball that he essentially drops, and it's going to end up moving down. Now, in these problems, you always need to remember that the exact place where you drop the ball and the motion starts, that position right there is called the initial position, y naught, and it's taken to be 0. I mean, of course, yeah, you're up in a tree and you know that you're like 40 feet up in the tree, but we don't ever use the fact that we're 30 feet in the tree to describe the motion. What we usually say is, here's the ball, we let it go. That is the 0 point. So as it goes down into negative y direction, the position will be more and more and more negative. And the velocity is going to increase because it's falling. So the velocity will also be more and more negative. So you should get used to the idea of seeing negative velocities and negative positions. It just means that you're down below here. So this direction is negative y, and up this direction is plus y. And if you throw the ball up, of course, we'll have some positive positions and velocities there too. So let's write down what we know, and let's solve this problem. What do we know? We know the initial position of the ball is equal to 0. How do we know that? Because the problem didn't say they threw it up. They just said they let it go. So its initial position was 0. What was its initial velocity? Well, that's also equal to 0. Before you drop it, of course, it's not moving. What is the acceleration? We already know what that is. It's always negative 9.8. And by the way, I already mentioned this about 25 times in the lesson on acceleration due to gravity. But when you drop an object, it doesn't matter if you're dropping a beach ball or a pencil or a pen or a bowling ball, or if you're throwing a bulldozer or a car or a skyscraper or a spaceship. It doesn't matter. It's always going to accelerate at 9.8 meters per second squared down. So you don't have to worry about the mass of any of this stuff. All right? And what we want to calculate is the position at 1, 2, and 3 seconds in the future, and the velocity at 1, 2, and 3 seconds in the future. So what we do initially is we say we're going to calculate it at 3 different times. So we first tackle the t is equal to 1 second time in the future. We want position and velocity. So the main equations of motion for position, or the main one, is y is equal to y naught plus v naught t plus 1/2 at squared. And again, I said you might see minus 1/2 gt squared. That's fine. I'm not going to ever solve problems like that. I'm going to write the equation of motion with an acceleration a, and then I'm just going to stick the proper acceleration in there in the next step. So let's do that next. What we know is that y, the position, is going to be the initial position, which is 0, plus v naught t. V naught is initial velocity, 0. It's going to be 1 second in the future. I'll stick a 1 in there. It's not going to matter. Plus 1/2. What is the acceleration? It's always negative 9.8 due to gravity. Time here is 1 second in the future, squared. So the position is going to be 0 plus all this stuff. So 1 squared is 1, multiplied by this, multiplied by this. You're going to get a negative, because of the negative sign here, 4.9 meters. I told you that you need to not be scared of seeing negative positions. It just means that you're 4.9 meters below the drop point. That's what happens after 1 second of free fall. It doesn't matter if it's a bowling ball. It doesn't matter if it's a beach ball. It doesn't matter if it's a pencil. It doesn't matter if you're dropping a spaceship or anything. It's always going to be negative 4.9 or 4.9 meters below the drop point after 1 second, because things always fall at the same rate in gravity. And we talked about that before. So at 1 second, we now want to calculate the velocity. What is the velocity? We're going to use our main velocity equation, v naught plus acceleration times time. So the velocity is what we're trying to calculate is equal to the initial velocity, 0, since we're dropping it, plus, what's the acceleration? Always negative 9.8. What is the time? 1 second. Whoops, I want to put a t in there. I want to put a 1 there. And so you multiply that out, what do you get? You get the velocity is negative from this, 9.8. What is the unit? Meters per second. So what you found is that after 1 second, this object is going 9.8 meters per second. The negative sign just means it's going down. It has to. You just dropped it. The negative sign means down, right? And the position means you're below the drop point. No matter what you drop, again, could be anything, without any air resistance, will always be going 9.8 meters per second after the first second. Makes sense, because acceleration is 9.8 meters per second squared, which means 9.8 meters per second is how much velocity you gain every second. After 1 second, that's what we have. Now let's go over here to the other board. And since we've done the first one, the others will be, trivially simple to figure out. At t is equal to 2 seconds, it's going to be the same exact song and dance, no difference. It's going to be y is equal to y naught plus v naught t plus 1/2 at squared. So the position is going to be the initial position of 0, initial velocity times 2 seconds, 1/2 negative 9.8 for acceleration of gravity, 2 squared. These are all 0. When you multiply all this together, you'll have a negative number. It'll be negative 19.6 meters. That's how far you're down below the drop point after 2 seconds. And then, in order to find the velocity, v is equal to v naught plus a times t. So the velocity is initial velocity of 0 plus negative 9.8 times 2 seconds. And so what are you going to get? Negative 19.6 meters per second. That's your velocity after 2 seconds. So notice the big jump here. You go from, after 1 second, 4.9 meters down, but after 2 seconds, you're much farther down, 19.6. After the first second, you're 9.8 meters per second. And then you're double that at 19.6, because every second you need to be gaining the same amount of velocity. So let's do the very last one, and that's going to be that at t is equal to 3 seconds, what do you have? We already have the equations written, so I'm not going to write them again. Y naught plus v naught times t plus 1/2 a, which is 9.8. It's going to be 3 squared, because that's time squared. Right? It's exactly the same calculation, so we do this, and what you have is you square this, multiply by this, you get a negative. What do you get? 44.1 meters. And then finally, the velocity, we can now calculate. V is equal to v naught plus a times t, which is the initial velocity of 0 plus negative 9.8 times 3 seconds. You multiply this, the velocity you'll get is negative 29.4. Oh, what meters per second? All right, the main thing you want to pull out of this is that the main reason we did this lesson, such easy problem first, is to let you know mostly that free fall motion, when things are falling down, they're accelerating at a constant acceleration, 9.8 meters per second squared down. So it means that you use the exact same equations of motion that we use initially for any of the other problems we did. We just have a negative 9.8 for the acceleration. And because of that, and because we're taking our drop point, when we start the problem off, we always take our reference to be the drop point. It means that if you're just dropping things, then it'll always have negative velocities and negative positions. That just means it's below the drop point. Later, when we throw an object up, for part of the time, the position and velocity will be positive because it's going up, and then for part of the time, the position and velocity will be negative because when it gets down below the drop point, it'll turn negative again. And that's how we keep track of if it's higher or lower than the drop point, by the sign. But the one thing I want to point out to you is, after 1 second, an object is only 4.9 meters down. After 2 seconds, it goes to 19.6 below the drop point. And after 3 seconds, way up to 44.1 meters below the drop point. Because, why do you think that is? It's because it's accelerating. It's moving faster and faster and faster. So when you get to over to 3 seconds, the thing is moving way faster than it was right after you dropped it. And that's why the position seems to increase so fast. Because it's not a line. The position, remember, is a parabola. It starts getting, because it's going faster, it starts moving more and more distance every second, and that's why it does this. And that's why when you drop something, it accelerates and starts covering more distance very, very rapidly. So here is our first problem in equations of motion due to free fall. Want to make sure you understand all positions are negative below the drop point. Velocities are negative below the drop point when they're going down. All motion of dropping an object in gravitational field is independent of mass. You don't see any mass in any of these equations of motion. There's no mass anywhere because it doesn't depend on mass. It doesn't matter what you drop, right? And then we're always going to ignore air resistance. So follow me on to the next lesson after you have solved these yourself, and we'll get some more practice with free fall accelerated motion problems in physics.